Today I'm going to talk about electromagnetic induction. I always tell my students if there's a big fancy name for something, it's probably important, and this is. It is all around us. It's how our generators work that make the electricity we use. It's how motors work. It even describes how our speakers work so we can listen to music. Many, many applications. I'll talk about another cool application in a minute, but right now I want to tell you a little bit about how electromagnetic induction works. What I have here is an ammeter that measures current, the movement of charges in a circuit. Here's a coil of wire. There's no current flowing because there's no battery. We need a battery to push the charges around. There's no battery, no current. Watch what happens when I take this big, strong magnet and move it across the face of this loop of wire. The current goes first to the left and then to the right. First to the left and then to the right. As long as it's moving, we get current to flow. Now watch what happens when I just hold it there. Nothing happens. No current flow. There has to be motion, either back and forth, or this way, in or out. There has to be motion between the magnetic field and the loop of wire to get the current to flow. So in a power plant, the wire is rotated like this. They spin it around and around and around in a magnetic field, and it generates our electricity. Here's a little handheld generator. I've got a light hooked up to it. And if I turn it around like this, you can see the light light up. And when I stop, it goes off. This is a little hand crank generator. I'm turning the wire with my hand in a magnetic field, and it's making energy. Let's take a look at big power plants. Some of them use gasoline or oil. They burn the oil, it makes heat, and that heat causes water to vaporize, to turn into steam, and the steam pushes a coil of wire around in a magnetic field. Nuclear power plants work the same way. A nuclear reaction generates heat, boils water, turns a coil of wire in a magnetic field, or we can use water pressure, like a dam. The water pushes through, turns the coil of wire in a magnetic field, or we can use the wind. Lots of different ways to do this, and we can even use solar power to do this. This is an image of currently the world's largest solar power plant in the Mojave Desert in Southern California. Those are not photovoltaic panels you see like you see on people's houses. This is very different. Those are mirrors. They're reflecting the sun's light back to the central tower. All that heat energy is boiling water. The steam pushes a coil of wire around in a magnetic field. On a large scale, this is how we generate electricity. Motors work very similarly. And you can even store information this way. Let's take another look at our coil. This is the north end of my magnet, and over here I have a piece of wood at the south end. So if I move the north end over the coil, first it goes to the left, and then it goes to the right. First to the left, then to the right. Now I'm going to turn it around. So the south end is facing the coil, and it goes to the right and then to the left, to the right and then to the left. So we get a different signal when the north end is facing the coil versus the south end. So we can store information this way in a credit card, for example. Magnetically, we can store the information. If the north end is facing up, we can call that a 1. If the south end is facing up, we call it a 0. We can store 1s and 0s. We can't store 2s, 3s, or 4s. We can only store 1s and 0s, but if we can store enough of them, we can make a unique number for everybody. This is a credit card reader. Looks just like the one at the supermarket, doesn't it? Okay, a little different. A couple of students here at Foothill College made this for us. There's a coil of wire here, and we're going to slide the credit card across it and pick up whether the north pole is facing up or the south pole. This is our credit card. Here's the magnetic stripe. Some of them have the north end facing up, that's the red dot. Some have the south end facing up, that's the black dot, and we're going to scan it through and see if the credit card reader can pick up which magnet is facing up. So every place there's a red dot, we should have the red LED lit up. How's that? Does it look right to you? It looks right to me. Let's change a few of them. Maybe somebody got a hold of our credit card and we need to change the number on it. So I'm going to flip a few of our magnets around. How about one more over here? How about? Okay, so we're going to run it again and see if it picks up the new credit card number. How's that? Did it work? Looks good to me. So, and lots of interesting applications for electromagnetic induction. We saw that generators and motors work this way. I told you this is how our speakers work, and a really neat application, credit cards. Next time you see somebody use a credit card at the supermarket or the gas station, you'll know why they have to swipe the card, why there has to be motion, because it's the motion between the magnet and the coil that creates the signal that we can pick up. Electromagnetic induction. It's all around us.